Hey, well, welcome back everybody to our Calculus 3 class notes. We're now on page 86 and we're in the first section of chapter 15 on multiple integrals. So right now we're talking about double integrals, and I already mentioned briefly that they can be thought of as volumes. So let me go over that a little bit more precisely. These certainly aren't pictures that I drew with anything I have. These are right out of our text, okay? So when a function f of xy is a positive function over a rectangular region R in the xy plane, so we have this rectangular region down here in the xy plane, and z equals f of xy is all positive, sitting above that plane, then we can interpret the double integral of f over that region R as the volume of the three-dimensional solid region over the xy plane, bounded by R and above by the surface z equals f of xy. So it's bounded by r below and above by the surface z equals f of xy. So you can imagine that. So if you have these, you break up that xy plane into rectangles that are fairly big, sort of like what I had back here on this picture, right? These are fairly decent sized big rectangles. Then I'm going to look at approximating the volume under this surface with this guy right here by adding up all of these, the volume of all of these different cubes. Now, if I take the rectangles to be smaller and smaller width and lengths, right, I get a better approximation and an even better approximation. And as I let n go to infinity, you can imagine that it just fills in that volume perfectly. Okay, so the entire volume is the limit as n goes to infinity of s sub n, which is the double integral over the region R of the function f of xy dA. Now dA can be thought of as dy dx or dx dy in this case. And as a matter of fact, Fubini's theorem says it's very simple here. If I have a rectangular region where x varies between the constants a and b and y varies between the constants c and d, then I really can integrate these in either order. So the double integral over R of f of xy dA is the integral from c to d with respect to y of the integral from a to b with respect to x of f of xy. So the way that works, or I could just switch those around. I could do dy dx, and so you kind of think of this as working from the outside in. This dx goes with the outside integral and the dy goes with the inside integral. Likewise, the dx goes with the inside integral here, and dy goes with the outside integral here. Now, when you evaluate these, you evaluate the inside integral first, leaving the outside integral alone, and then evaluate the outside integral. And I'll walk you through an example now and show you how that works.